Today I'm just going to clear up a few bits and pieces. We're going to look at a few applications from the wave theory that we've looked at in the last few lectures. So I'm going to start with a thing we call Stokes drift. So if you go back to, if we go back to a video that I showed you. So you see, I was trying to emphasize the orbital type motion of a parcel of water as it propagated in a way, as the wave propagated past it. But what you see also from this video is that it doesn't just go in a repeated cyclic motion. Every cycle, it kind of goes forward a little bit. Okay, and that is because the wave amplitude, as we have shown, the wave amplitude depends on the depth. And so when it's at the top of the wave, the amplitude is more, not just in the vertical, but also in the horizontal. So it goes forward a little bit more, then it goes back when it's at the bottom of the wave. And so, and this effect is most pronounced at the surface. So if you have something floating on the surface, it's gradually going to move in the same direction as the propagating waves. And so that's why you have driftwood and all sorts of rubbish arriving on the beach. It doesn't go as fast as the waves. The waves come to the beach much faster, but it does, slowly but surely, it does move in the same direction. And so we're going to try to calculate that speed, the speed at which it comes into the shore. That phenomenon is called Stokes drift. And so, quick calculation, we're going to go back to the expressions that we derived for the displacements of a parcel of water in the horizontal direction and the vertical direction. So my delta x and my delta z, and we said that they were describing an elliptic type motion. So the delta x is proportional to minus sine kx minus omega t, and the delta z is proportional to cosine kx minus omega t. And the coefficients here is the amplitude as a function of depth. And we showed that for deep water, we can say that the amplitude decays exponentially with depth. And we're going to assume that we're in deep water here. And so it's a circular orbit the water is doing. The horizontal amplitude is the same as the vertical amplitude, and they're both decaying with a depth scale 1 over k, so the wavelength divided by 2 pi. That's the vertical scale at which it decays. Right? So if we take these expressions for these displacements and we express the horizontal velocity, us, which is the average horizontal velocity over an entire cycle. And we base that on a Taylor expansion about these displacements, delta x and delta z. So our us is delta x times d by dx of u in the x direction, and our delta plus delta z times d by dz of u in the x direction. So that's how we construct our Stokes velocity, our Stokes drift speed. Now, the u by dx is, well, ux is d by dt of delta x, okay? So that gives us delta x times d squared delta x by dx dt plus delta z times d squared delta x by dz dt. So if we take these expressions and we do all that differentiation on these two expressions, well, what we get is something which is really quite clean. The ae to the kz times sine kx minus omega t, that's this part, times ae to the kz times k omega, because we're taking d by dz as well as d by dt. We've got the delta x. That's this thing, all right? And then we've got the double derivative of that delta x dx dt. So when we take the derivative with x, we have the k. And when we take the derivative with time, we have the omega. All right, so that gives us a k omega. So we've got this thing, ae to the kz squared. We've got the k omega, and then we've got the sine squared here, kx minus omega t. For the second term, it's the same thing. We get this expression for delta z, and then we multiply it by this double derivative, ae to the kz, k omega, and again, we have a squared cosine. So a squared sine plus a squared cosine just gives us 1. Sine squared plus cosine squared equals 1. So what we are left with then is 2 of these expressions. So we've got a e to the kz times a e to the kz. That's a squared e to the 2kz. Okay? So we've got an a squared e to the 2kz, and we've got a k omega in both parts of the expression. So we end up with the us is equal to this. us is equal to k omega a squared e to the 2kz. So that is our Stokes drift velocity. If you're interested in a piece of driftwood, so if you want something which is at the surface, then z equals 0. So this exponential will just disappear, and you'll just have k omega a squared. So the speed at which your piece of driftwood is drifting towards the beach depends on the amplitude of the waves squared. It depends on the wavelength, and it also depends on the frequency. So it depends on everything, pretty much.